Every liquid tells a different story of movement. Why does oil cling while water rushes? What invisible forces govern the speed at which a substance pours? Greetings everyone. Today we will delve into the molecular architecture that dictates this fundamental behavior. This is the mystery of flow, our journey into the heart of viscosity. Moving forward, let's establish the foundation of science communication. At its core, it is the clear and effective way of sharing scientific knowledge. This vital exchange can take many forms, from formal written reports and research papers to engaging spoken lectures and seminars or visually powerful graphs and figures. Ultimately, the main purpose of good science communication is to ensure that critical research is not only understood but can be replicated and practically applied. It serves as the indispensable bridge connecting meticulous laboratory discoveries with the tangible needs of the real world. So, why is this act of communication so vital? We can identify five critical reasons that impact society and progress. It is essential to educate the people to make informed decisions on matters that can affect their lives from health to environment. It works to make science more transparent, especially when funded by public or government resources, building critical trust. Good communication allows us to address urgent issues like a pandemic quickly and effectively by disseminating critical, life saving information. It serves to inform and educate companies to bring innovations to market, driving economic and technological advancement. And finally, it is necessary to educate decision makers with evidence based science for public policy creation, ensuring our laws and regulations are grounded in fact. Achieving high impact science communication requires a diverse set of skills organized across six key pillars. The first one is information retrieval, sourcing reliable data from experts, the library, or electronic databases. Second is scientific reading, comprehending the core knowledge found in articles, textbooks, and reports. Third is listening and observing, taking in information through video, demonstration, and lectures. The fourth is scientific writing, articulating research clearly in scientific essay, abstract, or report. The fifth is information representation, using visual tools like tables, schemes, and graphs to convey data efficiently. And the last is knowledge representation. Finally, communicating the findings through a scientific model, oral presentation, multimedia, or a poster. These elements collectively define the mastery needed to effectively transmit the scientific knowledge. Successful scientific communication is an ascending process, moving toward a higher degree of active participation. At the base, we have information and outreach. This is typically one way communication, such as a press release, where the target group is a passive recipient. It is the necessary starting point. The middle level is dialogue and engagement. Here, communication becomes a two-way street. All parties and active senders and recipients fostering conversation like a science cafe. Finally, at the peak, we find involvement and co creation. This is the highest level of participation where all the parties are actively influencing the research process itself. A powerful model exemplified by citizen science. The goal is always to climb this pyramid, transforming passive consumption of information into genuine, active public influence. The impact of proactive science communication is clearly visible through national achievements. These clippings highlight how landmark initiatives driven by organizations like ISRO and AIMS are communicated effectively to the masses. We see prominent coverage of India's solar mission, Aditya L1, and the success of missions like Chandrayaan 2, which captured the public's imagination. Similarly, significant medical breakdowns such as the historic use of robotic surgery at AIMS are front page news. These examples demonstrate that the government and scientific bodies are actively engaging with media to ensure that the national progress and technological advancements are understood, celebrated, and accessible to every citizen. Science communication makes complex ideas simple and relatable. It reminds us that science is not just about obscure labs and advanced formula. It's about explaining everyday phenomena in ways everyone can understand. And today, that everyday phenomena is the mystery of flow itself. Here we see the simple perfect moment. Winnie the Pooh enjoying his favorite thick, slow moving treat. But this simple pleasure hides a complex question. Winnie the Pooh is thinking that why does my honey have so much resistance to coming out of the vessel? Why does honey pour so differently than a glass of water? If honey and water are going to have a race, then who is gonna win? Let's put our liquid to the test. In this race, water is the clear winner as we can see. Water is flowing quickly and freely. We call this low viscosity. Honey, however, is the reluctant competitor. It flows slowly and resists movement intensely, demonstrating the high viscosity. To understand viscosity truly, think of it as a traffic inside a liquid. In a highly viscous substance like honey, the complex large molecules are crowded and constantly bump into each other, creating an internal traffic jam. This resistance slows it down. Conversely, in water, the molecules are small and move past to each other easily. The traffic is light, so it flows quickly and effortlessly. The traffic analogy clearly illustrates the difference between high and low viscosity at the molecular level. This visual brings the concept of resistance to life. On the left, we have water. Its low viscosity means it offers almost no resistance to the stirring rod. It swirls easily, confirming its smooth and fast flow. On the right, we see thick, dense syrup. Its viscosity is high, which results in a heavy drag against the stirring motion, physically illustrating the friction between its molecular layers. This demonstrates that viscosity is not just about flow. It is fundamentally about a fluid's internal resistance to any force attempting to change its shape or initiate movement. Viscosity is broadly classified into two types. The first one is dynamic viscosity and second one is kinetic viscosity. Let's dive deeper into the key distinctions between these two types of viscosity. On the left, we have dynamic viscosity, often represented by eta. It is the viscosity measured when an external force is applied directly to the fluid. Mathematically, as shown, it is defined by the relationship eta is equals to shear stress divided by the shear strain rate. This property directly quantifies the internal resistance between adjacent fluid layers as they move at different velocities. It's crucial for determining the frictional forces within the fluid. Dynamic viscosity is essential for calculating actual fluid flow velocity in pipes and channels, especially when dealing with pumps and pressure. Now, looking at the right, we have kinematic viscosity, which is represented by Greek letter V. Crucially, kinematic viscosity is independent of applied force. It's an intrinsic fluid characteristic. It is defined by simple yet powerful ratio V is equals to dynamic velocity divided by fluid's density. This measure tells us how a fluid flows under the influence of gravity. For example, it helps us to compare how quickly two different fluids will drain out of a container. Because it incorporates the fluid's density, kinematic viscosity can often be more informative than dynamic viscosity in analyzing overall fluid motion and performance in many engineering applications. In essence, dynamic viscosity is about the force of resistance and the kinematic Viscosity is about the flow relative to the fluid's mass. Not all liquids flow the same way. We categorize them into two main types based on how their viscosity behaves under force. First, we have Newtonian fluids. These are the saints of the fluid world. Their viscosity remains constant regardless of the stress or force applied to them. Excellent examples are water and simple oils. They flow predictably. Second, we have non Newtonian fluids. These fluids are the ones that throw tantrums. Their viscosity changes when a force is applied. They include ketchup, toothpaste, and oobleck. Non-Newtonian fluids category includes common household items like toothpaste, which only flows when you exert enough pressure to squeeze the tube, ketchup, which gets thinner when you shake it, and oobleck, the cornstarch mixture, which gets thicker and acts like a solid when you punch it. On a related note, the reciprocal of viscosity is a property called fluidity. The mathematical expression for viscosity comes from observing the force needed to move one layer of fluid over another at a specific speed. The formula for viscosity is denoted by eta, which is equals to F upon A into dV by dx, where F is the shearing force required, A is the area, dV by dx is the velocity gradient, which is the rate of change of velocity with distance between the fluid layers. Now let's look at the units of viscosity. In the CGS system, the unit of coefficient of viscosity eta is Dine-second per square centimeter, which is also known as poise. In the SI system, the unit of eta is Newton-second per square meter, which simplifies to Pascal second. Next, we will look at how viscosity is measured using Oswald viscometer. It is a U-shaped glass tube with a thin capillary in between. The device works by measuring how long a liquid takes to travel between two specific marks. A faster flow time indicates low viscosity, while a slower flow time indicates high viscosity. Here is a diagram illustrating the working principle of Oswald viscometer. First, the fluid sample is poured into the viscometer. Suction is then applied to pull the fluid up into the top reservoir. The suction is then released, allowing the fluid to descend by gravity. The time it takes for the fluid to flow through the capillary section, specifically from the start mark to the stop mark, is precisely measured. Beyond the precise laboratory instrument like Oswald viscometer, a qualitative comparison of viscosity can be made using simple methods. For method first to perform at home, we will need simple materials, clear container, liquid like water, milk and oil, and a dense pail like marble. We mark a specific distance and then time the marbles fall between those two specific points. Our results offer a clear qualitative comparison. You will observe the marble falling fastest in water, our lowest viscosity sample, and slowest in the oil, our highest viscosity sample. This simple experiment effectively demonstrates the concept of a fluid's resistance to flow. The next demonstration involves filling multiple containers, in this case plastic cups, each with a different liquid such as water, milk and oil. We then pierce a small hole near the bottom of each cup. By observing the liquid which exits the hole fastest, we are directly measuring its resistance to flow. The liquid that streams out first, like water, has the lowest viscosity, and the liquid that takes the longest to drain, like the oil, has the highest viscosity. as its internal friction resists being pushed through the small orifice. This stress provides a clear real-time visualization of how different fluids behave under the influence of gravity. Now let's examine the factors affecting viscosity for both liquids and gases. On liquids, increased temperature leads to decreased viscosity, making it flow easier, like heating honey. And on gases, increased temperature leads to increased viscosity. Talking over pressure, there is only a slight increase in viscosity due to incompressible nature of liquids, and increased pressure leads to increased viscosity in cases of gases. The third factor affecting viscosity is turbulent flow. It is a condition where the apparent viscosity of fluid changes. Next is flow conditions, which further affect viscosity, which includes multi-phase flow. In this, the combined viscosity depends on the volume of each phase present, and suspended particles, in which the presence of solids or impurities will hinder the fluid motion, generally resulting in a higher viscosity. And finally, the laminar flow. It is characterized by constant viscosity. Viscosity is a fundamental property with wide ranging applications in various fields. In food and beverages, it determines the texture of syrups and sauces, like honey being drizzled on pancakes. In oil and lubricants, it is critical for engine efficiency, ensuring proper coating and minimizing friction on moving gears. In human biology, the viscosity of blood is essential for cardiovascular health and flow through vessels. Viscosity is critical in industries like paint and coatings, ensuring the material has correct thickness for mixing and application. Viscosity control is also crucial in the production of the pharmaceuticals industry, where it ensures the correct formulation and consistency of syrups, liquid medications, and capsule coatings. And in the polymer manufacturing, where the flow properties of monomers and liquid polymers dictate the quality and characteristics of the final plastic products. In chemical manufacturing, viscosity control is crucial for mixing reactions and ensuring proper transfer and quality of chemical products. In the cosmetics industry, viscosity dictates the texture, stability, and spreadability of products like foundation, creams, and lotions. To conclude our look at applications, viscosity is also important in the creation of food colors and dyes, where the viscosity affects how they mix and distribute in liquids, and in printing and inks, where precise control over viscosity is required for the ink to flow properly through printer heads and adhere correctly to the paper. Let us now reach the heart of the matter. We begin by asking about the mystery of flow, and we conclude with a profound realization that is, viscosity is not just a scientific term, it is the silent engineer of our world. It is the unseen force that ensures your high performance engine runs smoothly. It is the master craftsman that perfects the texture of every bite of food you eat. And most crucially, it is the guardian of your very existence, controlling the flow of life through your bloodstream. To grasp the concept of viscosity is to hold the key to designing a smoother, a safer, and a fundamentally better world for all of us. This presentation was built upon reliable sources, ensuring the information presented is accurate and up to the date. Additionally, a variety of supporting visual and conceptual resources, including several images and GIFs, were drawn from reputable websites and scientific platforms, which are detailed here on the reference slide. This concludes to my presentation on the mystery of flow. I sincerely thank Dr. Charu Divedi for her guidance and every one of you for your time and kind attention. I am now open up to any questions you may have.